welcome back to another explainer. Today we're taking a dimensional journey. We're stepping right out of the flat 2D world of squares and plunging straight into the magical 3D world of perfect cubes. If you've ever wondered how numbers literally build the dimensions around us, well, you're in exactly the right place. We're going to uncover some truly mind-bending mathematical secrets that are just hiding in plain sight. Okay, so here's our roadmap for today. 1. Secrets of perfect squares. 2. Discovering perfect cubes. 3. Successive differences and patterns. 4. The magic of cube roots. 5. Ramanujan and taxicab numbers. And finally 6. The final challenge quiz. Let's just jump right in.
Section 1. Secrets of perfect squares. Building the 2D foundation.
So to really wrap our heads around the third dimension, we first have to totally master the second dimension. And we do that by looking at perfect squares. This is our foundation, right? Now, I want you to put on your detective hats for a second. We usually think of a square number as just a number multiplied by itself. 3 times 3 equals 9. But did you know every perfect square is actually hiding a sequence of odd numbers inside of it? No way, right? Let's look.
Just look at how this math breaks down. If we take the very first odd number, 1, the sum is 1, which is just 1 squared. Add the next odd number, 3, and you get 1 plus 3 equals 4, which is exactly 2 squared. Keep going. 1 plus 3 plus 5 equals 9. That's 3 squared. This brilliantly illustrates how adding consecutive odd numbers, starting right from 1, builds consecutive perfect squares layer by layer. It's kind of like building a 2D pyramid out of numbers. Section 2. Discovering perfect cubes. Leveling up to 3D.
All right, let's see how this builds into something even more robust as we cross over from flat planes into the immersive third dimension. So what exactly makes a cube perfect? Well, a perfect cube requires 3 identical dimensions: length, width, and depth. Mathematically, it's simply a number obtained by multiplying a number by itself 3 times. For example, multiplying 2 by 2 by 2 gives you 8. In algebra, for any number n, we just write n to the power of 3, or, as we usually call it, n cubed.
To really visualize this, imagine stacking actual building blocks. If you look at a larger 3D cube with an edge length of 4 units, you've got 4 blocks in width, 4 in depth, and 4 in height. Each square layer has 16 little unit cubes, and since there are 4 layers total, that larger cube is made up of exactly 64 smaller unit cubes. That is the physical reality of 4 times 4 times 4.
So the crucial point here is that numbers like 1, 8, 27, 64, and 125, these are our perfect cubes. They have actual volume. Meanwhile, a number like 9, which is just 3 times 3, is a square. It's entirely flat. It's stuck in 2D. You literally cannot arrange 9 smaller blocks to form a larger, perfect 3D cube. And hey, remember how squares are sums of odd numbers? Perfect cubes are too. 1 cubed is 1. 2 cubed is exactly 3 plus 5. 3 cubed is 7 plus 9 plus 11. The dimensions change, but that odd number magic, it absolutely remains.
Section 3. Successive differences and patterns. Drilling down to the core. We've seen how squares hide odd numbers, but what hidden mechanics do cubes have? Let's look back at squares for a second to set our baseline for a really fascinating mathematical tool called successive differences. If we write out the perfect squares, 1, 4, 9, 16, and subtract consecutive ones, we get this funnel of numbers. 4 minus 1 is 3, 9 minus 4 is 5, 16 minus 9 is 7. That's level 1, giving us our odd numbers. But if we find the differences of those differences, meaning 5 minus 3 or 7 minus 5, we drop to level 2. And look at that, the differences all magically stabilize at the number 2. Since squares are 2D, they stabilize at level 2.
Okay, let's apply this to perfect cubes and see how the pattern builds. Write out 1, 8, 27, 64. Subtracting them at level 1 gives us 7, 19, 37. Subtracting those at level 2 gives us 12, 18, 24. We haven't stabilized yet. The tension is definitely building. But compute the successive differences one more time. 18 minus 12 is 6. 24 minus 18 is 6. Boom! We reach level 3, and the difference becomes a constant 6. Because cubes are 3D, it takes exactly 3 levels of difference to hit rock-bottom stability. I mean, how beautifully elegant is that?
Section 4. The magic of cube roots. Unearthing mathematical origins.
If cubing a number builds it up into 3 dimensions, the cube root is the tool we use to tear it back down to its one-dimensional origin. But have you ever wondered where the word root actually comes from? This is a fantastic piece of history. In ancient India, mathematicians used the Sanskrit word mula, which literally translated to the root of a plant, to signify the basis or origin of a number. So Vargamula was the origin of the square, and Ganamula was the origin of the cube. As mathematical knowledge spread, this exact botanical metaphor spread like wildfire globally. Arabic scholars translated it to jither, and Latin scholars translated it to radix, both meaning the root of a plant. And that is exactly why we call it a square root today.
Section 5. Ramanujan and taxicab numbers, a legendary mathematical anecdote.
Now, let me share one of the most incredible historical anecdotes in mathematics. It features the genius Srinivasa Ramanujan and a simple, everyday hospital visit. The story goes that British mathematician G.H. Hardy arrived at the hospital in a taxi to visit an ailing Ramanujan. Hardy remarked that his taxicab number was rather dull and said he hoped it wasn't a bad omen. Well, Ramanujan, whose mind just saw deep patterns everywhere, instantly replied with a brilliant observation, completely refuting Hardy right there on the spot.
The allegedly dull number written on the side of that London taxicab? It was 1729. Thanks to Ramanujan's completely off-the-cuff genius, this specific integer is now permanently anchored into math history.
And this perfectly illustrates why 1729 is the absolute smallest number that is the sum of 1 cubed and 12 cubed, and simultaneously the sum of 9 cubed and 10 cubed. This spontaneous realization birthed an entirely new category in mathematics called taxicab numbers. The very next taxicab numbers you'll hit as you count up are 4104 and 13,832. It just goes to show that there are no boring numbers, only numbers whose secrets we haven't unlocked yet. Honestly, that's a pretty great perspective to take into everyday life.
Section 6. The final challenge quiz. Become the math genius.
All right, you've absorbed the theory, you know the history, and now it is time for the final boss of this explainer, a rapid-fire quiz to test your new 3D skills. I highly encourage you to literally grab your notebooks and a pencil. Treat these next 5 questions like levels in a video game you've got to beat. Don't just wait for me to give the answers. See if you can work them out. Let's go.
Here are your first 2 challenges. Level 1. Find the cube roots of 27,000 and 10,648. Here's a hint. Look at the zeros for the first one and use prime factorization for the second. Level 2. The number 1,323 is not a perfect cube. What single number do you need to multiply it by to make it 1? Think about grouping prime factors into sets of 3.
And boom, let's look at the solutions. For level 1, the cube root of 27,000 is 30, because 30 times 30 times 30 gives you the 27 and the 3 zeros. The cube root of 10,648 is 22. Fantastic job if you got those. For level 2, the secret multiplier you need is 7. If you factor out 1,323, you get 3 3s but only 2 7s. To complete that 3D cube, you desperately need one more 7.
Okay, here is the final rapid-fire round with levels 3, 4, and 5. Level 3. Quickly, what are the cube roots of 64, 512, and 729? Level 4, can you instantly tell me what 10 cubed is without using a calculator? And level 5, a conceptual true or false. The cube of any odd number is even. Lock in your answers. Amazing job if you got these. The roots for level 3 are 4, 8, and 9. For level 4, 10 cubed is simply 1,000. You literally just write a 1 and add 3 zeros. And for level 5, that is absolutely false. The cube of any odd number remains odd. An odd times an odd is an odd, and multiplying it by a third odd keeps it odd forever.
We've thoroughly explored and mastered the third dimension today. We traced the ancient roots of the math, stabilized those successive differences, and learned exactly how to build and unbuild perfect cubes. But all of this structure just leaves me wondering one thing. If squares stabilize at 2 levels and cubes at 3, what kind of mind-bending patterns are waiting for us when we multiply a number by itself 4 times and step into the 4th dimension? Well, that's something for you to think about. Thanks for learning with me.